Container Storage Interface defines a set of common interfaces to support different types of file and block storage for containers running in Kubernetes clusters. There are more than 100 CSI drivers supporting a variety of storage systems. There's also an ongoing effort of adding object storage in Kubernetes. Xing Yang, lead at VMware, will give an overview of the current state of Kubernetes storage and discuss what might be coming in the future. Over to you, Xing.
Hello, everyone. Today, I'm going to talk about Kubernetes storage. My name is Xing Yang. I work at VMware in the cloud storage team. I'm a co-chair of CNCF Storage Tag and a co-chair of Kubernetes Storage SIG. I also co-lead the data protection working group in Kubernetes. Here is today's agenda. I'm going to talk about Kubernetes storage in the scope of the storage SIG. I will mainly go over Kubernetes CSI features, which support file and block storage. At the end, I will also briefly talk about Kubernetes COSI, which is to introduce object storage support in Kubernetes. It is targeting alpha in 1.22 release. Kubernetes SIG storage scope is in the storage control plane. It provides a way for containers in the pods to consume block or file storage. This can be persistent storage that lives beyond a pod's lifecycle, or it can be ephemeral storage, which becomes available when the pod is started and goes away when the pod goes down. This includes managing the lifecycle of the volumes used by the pods, looking at how to influence the scheduling decisions based on topology and capacity, and managing storage capacity, providing the ability to expand volume if a volume runs low in space, etc. Here's a diagram that shows various Kubernetes components, the CSI driver, and the storage system that is used to persist the data on the volumes. Here we have Kubernetes Controller Manager on the master node. CSI driver controller plugin is deployed together with Kubernetes CSI external provisioner, external attacher, external resizer, and external snapshotter sidecars. The Kubernetes CSI sidecars are watching Kubernetes API objects such as persistent volume claims, persistent volumes, persistent and volume attachments, volume snapshots to detect create volume, attach volume, volume expansion, or volume snapshot requests. The sidecars called the CSI driver, and the CSI driver communicates with the storage system to complete those volume operations. On Kubernetes worker nodes, we have Kubelet and the CSI driver node plugin deployed together with the node driver registrar sidecar container. Node driver registrar fetches driver information by calling node getinfo from a CSI endpoint and registers the CSI driver with Kubelet on that node. Kubelet directly issues CSI node getinfo, node stage volume, and node publish volume calls against the CSI drivers to get info and mount volumes. In CSI spec, we have RPCs for volume lifecycle management. This includes provisioning support such as create and delete volume, and RPCs that make sure volumes are available for a pod to use. This includes controller publish unpublished volume, node publish unpublished volume, and node stage and unstage volume. Now I'm going to talk about a feature that helps with storage capacity management. This is volume resize. This feature has been in beta for quite some time now. There are still some issues we're trying to address before moving it to GA. One issue we're trying to address is recover from resize failure. Sometimes a user may expand a PBC to a size which may not be supported by the underlying storage system. Currently, there is no way for a user to request a smaller size to recover from this failed resize attempt. So the goals are to allow users to cancel previously issued volume expansion requests, assuming they are not yet successful or have failed, and allow users to retry expansion requests with a smaller value than the original request size. This is targeting alpha in 1.23. Design discussions are still ongoing. Moving on to volume snapshot. This feature is GA since 1.20 release. It provides a basic building block to support data protection in Kubernetes. It includes volume, snapshot, CRDs, and other common components, such as the snapshot controller and the validation webhook. We strongly recommend Kubernetes cluster distros to install these components because they are independent of CSI drivers. And there is an external CSI snapshot or sidecar that should be deployed together with the CSI driver. The implementation of create snapshot, delete snapshot must support idempotency. The CSI also support cloning. A clone is defined as a copy of an existing Kubernetes volume. It is independent of the original volume. To implement volume cloning, the CSI driver must implement clone volume controller capability. Also, in the plugin's create volume function, it needs to check volume content source in the create volume request and create a volume from that source. And next, I will talk about volume mode. This defines how a container uses a volume. There are two persistent volume modes. The first one is file system, which indicates the volume will be formatted with the file system. This is corresponding to mount volume capability in CSI spec. Volume will be mounted using a specified file system and appear as a directory inside the container. The other mode is block. This means the volume will not be formatted with the file system and will remain a raw block device inside the container. This is corresponding to block volume in CSI spec. Now let's take a look of access modes. CSI spec supports several access modes as shown here. The single node writer means the volume can only be published once as read-write on a single node at any given time. But there's a problem on how this access mode is used during node publish volume, which is typically when volume mounting is performed. The CSI spec defines that when node publish volume is called for the second time for a volume with a single node writer access mode and with a different target path, the plugin should return failed precondition. For CSI plugins that strictly adhere to the spec, this guarantees that a volume can only be mounted to a single target path, which means single node writer restricts access to a single pod on a single node. This behavior conflicts with the original definition. Because of this conflict, we do not have an access mode that represents multiple writers on the single node. To solve this problem, in CSI 1.5, we introduced two new access modes: single node single writer and single node multi-writer. In Kubernetes, there are three persistent volume access modes. They are read-write once, read-only many, and read-write many. We are proposing to add a new read-write once pod persistent volume access mode, targeting alpha in 1.22. If CSI driver supports this new access modes, then a persistent volume access mode read-write once pod is corresponding to single node, single writer in CSI. If these new access modes are not supported, then we can use this new access mode. For read-write once, it is corresponding to single node multi-writer if CSI driver supports this new modes. Otherwise, it is corresponding to the existing single node writer, which is the existing behavior. Now let's take a look of topology. Topology can be used to influence scheduling of pods. Some storage systems expose volumes that are not equally accessible by all nodes in a Kubernetes cluster. Instead, volumes may be constrained to some subset of nodes in the cluster. The cluster may be segmented into racks or regions or zones. To enable Kubernetes to support these storage systems, the CSS spec enables the ability for CSI driver to opaquely specify where a particular node exists. For example, node A is in zone 1. And the ability for Kubernetes to influence where a volume is provisioned. For example, I want to provision new volume in either zone 1 or zone 2. And the ability for CSI driver to opaquely specify where a particular volume exists. For example, volume X is accessible by all nodes in zone 1 and zone 2. Kubernetes and the external provisioner use these abilities to make scheduling decisions. To support topology in a CSI driver, the CSI driver must implement the volume accessibility constraints in the plugin capability. The plugin must fill in accessible topology in node getInfo response, and this information will be used to populate the CSI node object, and the topology labels will be added to the node object. The topology information will be passed in to the create volume call. In the storage class, there are 2 volume binding modes that are supported. If immediate is set, then the external provisioner will pass in all available topologies in the cluster for the driver. If wait for first consumer is set, then the external provisioner will wait for the scheduler to pick a node. The topology of that selected node will then be the preferred topology. Now let's take a look of storage capacity tracking. This feature is beta since 1.21 release. Traditionally, the Kubernetes scheduler was based on the assumption that additional persistent storage is always available everywhere in the cluster and has infinite capacity. But this is actually not true. The topology support that I mentioned earlier addressed the first problem. The storage capacity tracking addressed the second problem. It adds an API for CSI driver to report storage capacity and uses that information in the Kubernetes scheduler when choosing a node for a pod. This works for both local volumes and other topologies based on regions, zones, and so on. To support storage capacity tracking, a CSI driver needs to implement controller capability, get capacity. The external provisioner periodically calls get capacity. There are 2 deployment modes for the external provisioner. The default is the central controller. Get capacity request will be called for each known topology segment. And the second mode is distributed mode, where there will be 1 external provisioner per node. Also in CSI 1.4, we added 2 new fields in get capacity response. They are maximum volume size and minimum volume size. These new fields are more precise than the existing available capacity. because fragmentation might prevent creating a single volume that uses all available capacity. On the Kubernetes side, there is a CSI storage capacity API object. It is a namespace object created by the external provisioner. The capacity and the maximum volume size in the CSI storage capacity object are populated based on get capacity response from the CSI driver. There is also a Boolean flag storage capacity in CSI driver spec. It is off by default. It should be set to true to support storage capacity tracking. Kubernetes supports ephemeral volumes whose lifecycle is tied to a pod and can be used as scratch space. For example, the built-in empty-dir volume type, or to load some data into a pod, for example, the built-in config map and secret volume types or CSI inline volumes. The generic ephemeral volume feature allows any existing storage driver that supports dynamic provisioning to be used as an ephemeral volume with the volume's lifecycle bound to a pod. It can be used to provide scratch storage that is different from the root disk. All storage class parameters for volume provisioning are supported. All features supported with persistent volume claims are also supported, such as storage capacity tracking, snapshotting, cloning, and volume resizing. This feature is a beta since 1.21. Here is an example of a generic ephemeral volume. We set volume type to ephemeral in pod inline definition. Here is an example of CSI ephemeral volume. We set volume type to CSI in pod inline definition. Let's see what are the differences between these two types of ephemeral volumes. For CSI driver to support CSI ephemeral volumes, it must be modified or implemented specifically for this purpose. A CSI driver is suitable for CSI ephemeral inline volume if it serves a special purpose and needs custom per volume parameters, like drivers that provide secrets to a pod. A CSI driver is not suitable for CSI ephemeral volumes when provisioning is not local to the node, or ephemeral volume creation requires volume attributes that should be restricted to an administrator, for example, parameters in a storage class. Ephemeral volume, the generic ephemeral volumes, on the other hand, make the normal volume API storage classes, persistent volume claims usable for ephemeral use case. A CSI driver is suitable for generic ephemeral inline volumes if it supports dynamic provisioning of volumes. No other changes are needed in the driver in this case. Now I'm going to talk about this other feature, volume health monitoring. Without volume health monitoring, Kubernetes has no knowledge of what happened to the underlying volumes on the storage system after a PVC is provisioned and used by a pod. With this feature, CSI driver can communicate with storage systems and find out what happens to the volumes and communicate back to Kubernetes. So Kubernetes can report events on PVCs or pods if volume conditions become abnormal. This feature includes two parts. There is an external volume health monitoring controller that is a sidecar deployed with the CSI driver to monitor volume health from the controller side. Kubelet also monitors volume health from the node side. The external health monitor controller calls either list volumes or controller get volume CSRPC and reports volume condition abnormal events with messages on PVCs if abnormal volume conditions are detected. There is also a node watcher component in the controller. If the node watcher is enabled, an event will be reported on PVC to indicate that the pods using this PVC are on a failed node when a node failure event is detected. The controller-side volume monitoring has been alpha since 1.19. When volume health was first introduced in 1.19, there was an external health monitor agent that monitors health on the node side. In 1.21, we made a design change to avoid duplicate CSI calls. Kubelet already calls node get volume stats to retrieve volume metrics. In addition to that, it now also retrieves volume health condition through node get volume stats CSI RPC call and reports volume condition abnormal events with messages on pods if abnormal volume conditions are detected. Only CSI drivers with volume condition node capability can support volume health monitoring in Kubelet. We added a new alpha feature gate, CSI volume health, in 1.21 to introduce this feature in Kubelet. The next feature I'm going to talk about is pod service account token. This feature allows CSI drivers to impersonate the pods that they mount the volumes for. This improves the security posture in the mounting process without handing out unnecessary permissions to the CSI driver's service account. This feature is especially important for secret handling CSI drivers, such as the secret store CSI driver. Since these tokens can be rotated and short-lived, this feature also provides a way for CSI drivers to receive node published volume RPC calls periodically with a new token. Next, I'm going to talk about FSGroup. FSGroup is a way for Kubernetes to allow pods to access data on their volumes. If a new volume is provisioned for pod, by default, only a root user can write to the volume. However, we would like pods to run as unprivileged users. FSGroup is an optional group ID in pod security context. Kubernetes will run the pod with that FSGroup ID and change ownership of all the files on the pod volumes to be owned and writable by the group before starting the pod, so that the pod can rewrite on the volumes. However, there are problems with FSGroup. It can slow down the pod's startup time. If there are lots of files on a volume, Kubernetes will do a recursive change of all files on the volume every time the pod starts. So we introduced this skip volume ownership change option, so a user can opt out by setting a flag in the pod security context, so that FSGroup will only be applied the first time the pod starts to get the right permissions. And after that, pod starts will be fast. This feature is beta since 1.20. Another problem is that sometimes FSGroup cannot be applied to volumes at all. For example, if the volume is an NFS share with a root squash option. In Kubernetes 1.20, we have this beta feature for CSI driver to opt in or out of the recursive modification and avoid needless modification attempts. This helps reduce volume mount time. The third problem is that some storage system can apply FSGroup more efficiently by applying it to the whole volume, for example, as a mount option. So we're introducing a feature in 1.22 to delegate FSGroup to CSI driver instead of kubelet. The last Kubernetes CSI feature that I'm going to talk about is CSI Windows. CSI Windows is targeting GA in 1.22 release. There are challenges for CSI drivers to work on Windows. Windows containers are not privileged. However, CSI drivers need to perform privileged operations such as mount, unmount. So the solution is to have a privileged proxy binary named CSI proxy that runs as a native Windows process on the Windows nodes. CSI proxy will expose an API through gRPC over named pipe for executing privileged storage-related operations on Windows hosts on behalf of Windows containers, such as CSI Node plugins. Only CSI Node RPCs need to be implemented by CSI drivers to support Windows. I talked about lots of existing CSI features. Here are some features that are still in design phase. The first one is volume group. This is to have a way to group volumes used in the same application together to be able to create consistent group snapshot. Sometimes users want to be able to take a crash consistent snapshot because application QoS is not possible or too expensive. Another use case for volume group is to use this for volume placement. This is still in design discussions. Another feature that is in very early design stage is CBT, change block tracking. This is important for efficient backups. The third one I want to mention here has to do with non-graceful node shutdown. There is a proposal to provide a force detach option for storage backends to do some cleanups after a non-graceful node shutdown. This is still being reviewed. So I have talked about CSI. Now I want to talk about COSI, Container Object Storage Interface. This is a sub-project in Kubernetes 6 storage, trying to bring object storage support in Kubernetes. This is modeled after CSI, but it is different from CSI. CSI is for provisioning file and block storage. File or block volume is mounted on a pod so that a pod can access to the volume. COSI is for provisioning object buckets. An object bucket cannot be mounted. It is accessed through the network. Also, object storage has more fine granular access control. COSI defines Kubernetes APIs to provision object buckets and provide access. COSI also provides gRPC interfaces so that our storage vendor can write a plugin to provision object buckets on their backends. I won't go into details for COSI. I think there's another talk tomorrow about COSI. If you're interested, please attend that session. This is the end of this session. Thank you all for attending. Goodbye.
Very much, Sheng, for that lovely session. If we do have any questions, we can take a few questions now. Let's just say if we have any questions. From the attendees, can we have some questions? I'm just going to give it a few more moments. I see some typing activity. I'm just going to give it a few more moments. Any questions on Kubernetes CSI? All right, so one question that we have, I'm just going to post it here. In the CSI roadmap, is there anything specific for performance monitoring enhancements, especially storage levels?
I have not seen any. I mean, the only thing is the boarding house, but that's not really monitoring the performance. I have not seen anything like that yet.
Okay. All right. And I believe at the moment, I don't see any more questions, but thank you so much, Shing. It was really lovely to see you again. It's been a while, but we've always been connected via SODA. So thanks again, and we hope to see you at more future events and collaborate on CSI.
Thank you.
Thank you. And bye-bye. With that, we will now move to the next session, that is the penultimate session of the day-night, that is user-defined cloud workflow policies by Paul Special. Let's all now move to the next session, please.